they are looking for any reason not to spend money. And they will be the death of your company. So look for, as much as you can. Look for bosses that are looking to drill wells, because that's how you make money. And basin evaluation is a big part of that. You look at it and you say, where am I? I know I've got, in this basin, I've got 3 shales that are potential source rocks. Where do I drill in the basin to find oil? Has any of it been buried long enough to generate oil? Has it been buried so long there's no oil left in the basin? Or has it not been buried enough to generate any hydrocarbons? That's going to have to be one of the first discriminators you're going to use in deciding whether a new basin is worth proceeding on. You're going to use it in prospect evaluation. Are you looking at a structure that's the right age? Say, for example, your oil generated 160 million years ago. Your oil generated and migrated 160 million years ago. But regional forces, your structural analysis says that the structure you're wanting to drill didn't develop until 65 million years ago. What are your chances of there being oil trapped in that structure? Any ideas? This is a two-way street. You can talk. It's not very likely that there's going to be any oil left in that structure if the oil migrated 100 million years before the structure got there. That oil has gone somewhere else. So it's important to determine if your structure is the right age. And finally, kind of a tie back to the basin evaluation, are we in the right part of the basin? I've made maps of a good bit of the East Texas basin trying to put a play into the right part of the basin so that I would know that I was in the oil window instead of the gas window. Because right now, with oil at $100 a barrel and gas at $2.50 an MCF, there's not much economics in drilling deep, expensive gas wells. So you'd better be right the first time. And you don't want to go tell your boss, I want to buy $1 million worth of acreage in this area, and say, oops, I'm too deep. We need to move half a county to the north to get shallower to be in the oil window. Bosses take a dim view of that. So, on the other side of the coin, in addition to prospect evaluation of prospects that other people have done, is prospect sales, which is just the flip side of that. Demonstrating that you're in the correct age and the correct place in the basin. All of these things tie together. There are a lot of other ways that carriage and maturation is defined. I happen to personally be a fan of the TTI method because it's cheapest, it's easiest, it's repeatable. But there are a lot of other ways that it's done. And so we'll briefly go through some of these. TOC, this is the concept, it's total organic carbon. This is not the carbon that's trapped in a limestone as a carbonate ion. This is organic carbon. This came from plants and critters. And it's measured by weight percentage. As a rock matures, as a rock dewaters, as a rock generates hydrocarbons and they migrate out of it, this is a number that will change. the original TOC is not what it's going to be after migration. So a very important point to remember when you get out into the workforce and you start talking about TOCs and somebody says, well, we went up here to the outcrop and measured the TOC and it's 14%. This is a great shale. Well, what is it down there in the middle of the basin? How much of it has been converted to hydrocarbons? How much of it has migrated out of it? The two numbers are not going to be the same. So you've got to understand that TOC is not a single point. It is a spectrum. And it's going to vary from one very local place to another because of depositional differences. So that's not a one thing. I'm going to take a little chunk of shale and that's good for a whole basin. That little chunk of shale is representative of that little chunk of shale. Second, vitrinite reflectance. This is a scale that was designed for coals. As coals mature, as they're buried, and coals, remember, are type 3. And this isn't a marine kerogen. As coals are buried, as they dewater, as they go from subbituminous to bituminous all the way up through anthracites, the little pieces of shale or of coal get shinier and shinier. And there's a scale called vitrinite reflectance that has been applied to coals to look at them and say, what grade are these coals? That's all it comes from. But remember, again, that has some caveats to it. That was built around type 3 kerogens, not type 2 kerogens. Yes?
So is that something you get from your mud logs or core samples?
Normally what you're going to do with those is you're going to take your samples and you're going to send them off to a laboratory, and that is part of the laboratory analysis because you need somebody that has looked at them a lot to give you a good idea of what really compares to, so you're comparing apples to apples, I guess. TOC is also a laboratory measurement. You're going to send that off to a geochemical laboratory, and they're going to measure that as well. In fact, all of these require lab work. These are not the sorts of things that you can really do accurately yourself. That's another reason that I like the TTI, because that's something I can do myself. Right now I find myself in a very small company, which I absolutely love, but we don't spend extra money for anything if we can help it. So if I can do the work, then we're not paying out dollars to somebody else to do it. Thermal Alteration Index, or TAI. This is another one of those coal-based scales. It was based on the color of spores and pollen as they matured. As the coal went from subbituminous all the way up to anthracite, the spores and pollen changed colors. And that was this Thermal Alteration Index. Rocky Valve is a different system. You take little chunks of rock and you heat them up and you drive off all of the kerogen that you can. You measure the carbon monoxide that comes off of it. The carbon to oxygen and hydrogen to oxygen and carbon to hydrogen ratios all determine which of those original types of rock we were looking at. Because if you go back to this again, you have a hydrogen carbon index, an oxygen carbon index, And if you get a measure of this and this, it'll put you right there, or it'll put you right there, or it'll put you right there. It's going to tell you where you fit on this chart. So Rocky Val is a little different than the others. So
when you talk about condensate, where does that fall in?
condensate would be in this area right in here. You've gone from immature kerogen to oil in this area to wet gas, which is gas with condensate, to dry gas in this area right in here. So your condensate's right in there. And finally, there was a guy in '75 that decided to try and take all of these scales that we've looked at and called it the level of organic metamorphism. I think it was just a good way to get his name in print. But he was really trying to extend these coal-based systems and scales into type 2 kerogens so that they could be used in the petroleum industry. And he called this his level of organic metamorphism. And so this was a fancy chart that came out of all of Hood's work. Evan, I don't know if you want to put a test on this for him for next week or not. But what you see on here, this was his level of organic metamorphism over here. This was the coal scales. Then here was this spore carbonization, thermal alteration index, TAI, and vitrinite reflectance. He was just trying to push these numbers down a little further so they would be useful in the petroleum industry. Very few people use LOM. By far and away, vitrinite reflectance, Rocky Val, and the TTI are the three that will be used the most. I've seen one or two people reference this thermal alteration index, but I think they had a particular axe to grind, and so that was not something that I worried about too much. If you understand Rocky Val, to get back to the kerogen type, if you understand the TTI, vitrinite reflectance, those are the only ones you're going to have to worry about a great deal. So, now that we've taken kerogen and turned it into oil and gas, there's some other things we need to look at, because the maturation of the hydrocarbons are not the only thing that are going on in the shales. You add heat and pressure to the shales, at the same time you're generating hydrocarbons, you're also changing the structure of your shales. Shales have multiple dewatering events. The first one is very, very early, and that's because when a shale is initially deposited as a bunch of clay, there's a lot of space between the individual flakes of clay. That is very early dewatering, and that's not what we're talking about. But as that rock continues to get buried within the crystal lattice, especially of montmorillonite and the clays related to montmorillonite, you have a process called illitization. Big fancy word for meaning montmorillonite gets heated up enough that it drives out the water and it changes its crystal structure from montmorillonite to illite. That's all that fancy word means. Well, believe it or not, the amount of heat and pressure that it takes for this montmorillonite to illite transformation is just about the same amount that it takes to generate oil. And oil generation starts at about 50% of this illitization water loss and ends at about 75% of the water loss. Well, that's pretty important because you have all that extra water to help you carry the oil out of there. And that's a big deal because that helps generate additional pressure and it helps let everything flow out of the rock. So this is one of those very fortuitous things that happens to be just about right. Oil migration and illitization take place at just about the same time, so you have water migrating with the hydrocarbons. What happens when you squeeze the water out and you squeeze the oil out? It changes the density of your shale. Your shale density increases up to a point. Your shale density is going to increase until the boundary seals on the shale don't allow any more shale water or hydrocarbon to leave out of the shale. It's a pressure phenomenon. Basically, the boundary pressure exceeds the pressure within the shale and migration ceases. When migration ceases, you still have the last 25% of the water coming out of the illite. You're also still heating everything up. You have oil beginning to convert to condensate and gas. All of these things are generating increased pressure inside the shale. And a bunch of things happen that we're going to go through all of this. One of the things that happens is the generation of carbonic acid, which happens about the same time all of this is taking place. Another thing that happens is this thing we're going to call abnormal pressure. There's probably a lot better terms for that, but that term originated as a driller's term. And I'm going to take an aside here and explain abnormal pressure. Is there anybody here that, maybe I should ask first, is there anybody here that doesn't know what abnormal pressure is? Okay. Abnormal pressure is predicated on the concept that as you drill a well in the ground, the deeper you go, the more pressure there is trying to push fluid into the well. That pressure is going to increase at roughly a ½ pound a foot. It's not exactly, but it's close enough for our work. So at a depth of 2,000 feet, that bottom hole pressure should be about 1,000 pounds. At 10,000 feet, it should be about 5,000 pounds. But what happens to cause that is a vertical movement of pressure. Basically, you have sufficient permeability to let your pressure equalize with depth. So that a simple way to look at it is you are drilling into a column of fluid because the pressure, that ½ pound per foot, is roughly equivalent to the weight of a column of slightly salty water at a particular depth. So it's like you're just drilling down through 10,000 feet of brackish water to ocean water. What happens when the shale seal becomes so effective that you no longer have that vertical permeability. Now you have water, gas, and pressure trapped inside the shale. And you're essentially, the best analogy for it is, you're no longer drilling in a column of water, because now the fluid in the well that you're drilling into is not only supporting that column of water, but it's supporting some of the rock above it. So now, whereas a standard mud weight for most wells is around 10 pounds per gallon. Pure fresh water weighs 8 pounds per gallon, plus or minus. We add material to it so that we always maintain a positive pressure to hold formation fluid in the formation. So we're going to have a mud weight that is heavier than any pressure that might push into the well. As we drill into abnormal pressure, we have to increase our mud weight above that normal 10 pound per gallon to 12, to 14. In very rare cases, I've seen places where they had to use 20 pound mud. Pressure was double what it should have been at that depth. There was such a good seal, so much phase change. In those cases, it was almost always dry gas. Oil had been locked in place, had gone from oil to condensate to natural gas, and the phase change from liquid to gas, the temperature had created huge pressures. Those are relatively uncommon, but it is all tied back to Kerogen maturation. So this concept of abnormal pressure is something that we will come back to in a little bit more, but I wanted you to understand what it is. Let's see, make sure I haven't forgotten anything here. But shale density is one of the ways that we track abnormal pressure, because as you're drilling down, you can weigh the density of shales. And they do this, they have a column of fluid that is graduated by density, heaviest on the bottom, lightest on the top. You drop a piece of shale in, and it'll go down and find its own equilibrium. And that'll tell you what that shale density is. As you go down through this normal pressured section, shale density will continue to increase until you reach this boundary. And when you reach the top abnormal pressure, that shale suddenly gets much lighter, because it hasn't been able to compact as much as it would like to. So, have I befuddled you on that sufficiently? Not? Okay. Well, then we'll go on to something else. Organic acids. During the maturation of hydrocarbons, carbonic acid is released at the same time. I don't begin to understand the organic geochemistry that goes into it. I don't want to. That's not my job. But needless to say, it happens. And this is very important. This is not one of those things that people think about a lot, but they need to. Because if you have a reservoir, especially a sand reservoir that has a calcite cement in it, carbonic acid, even though it's a weak acid, will dissolve calcite cement in what would ordinarily be a pretty tight sandstone. And it migrates at about the same time, or sometimes just before, the hydrocarbons. So you get carbonic acid in a rock that has been buried for 50, 80 million years. It's pretty tight. It may be 10% porosity. That may be all that's left in it. Then all of a sudden, here comes the hydrocarbons to migrate into it, and leading the pack is all this carbonic acid. As soon as it sees that calcite, it starts dissolving the calcite. There's a very, very good field in Polk County, down east of Livingston. It's called AA Wells Field. It is Eagleford in age. It's down at almost 16,000 feet, an area where normally you'd expect porosities to be in the 10 to 14% range. It has porosities over 20%. And it's because carbonic acid migrated in before the hydrocarbons and has etched away a lot of the pre-existing calcite cement. So, carbonic acid is definitely your friend.
Have there been times in reservoirs where you think that there is the opportunity for carbonic acid to increase the porosity and it didn't?
Yes, there have been places, and I suspect, I'm not certain, I think in some of those places it may be that the carbonic acid was used up, for lack of a better term, deeper in the section before it got that high. Because most of the places that I've seen that, it was reservoirs near the top of a big limestone sequence. So it may be that the hydrocarbons, or that the carbonic acid was used up and spent before it got to the reservoir. It may be that there are places where the geochemistry does not generate very much carbonic acid. But I will say in sandstones with calcite cements, it is very common to see evidence of late-stage dissolution of calcite cement right before hydrocarbon migration into the reservoir. And when you get enough hydrocarbon into the reservoir, it just about stops any other diagenesis. You may still have a water-wet rock and have a small amount of ionic transfer, so you can get a little bit of diagenesis, but you don't have the big volumes of water migrating through the reservoir anymore. So generally, and there are always exceptions, but generally, when you get migration into a reservoir, that is just about the last stage of diagenesis, unless the oil is retransported to another